Okay, interference of waves. So in this slide, we want to define constructive and destructive interference, determining the outcome of two waves interfering. Let's just watch this video.
I can never remember I can never remember how to perfectly format my citations.
Just click Get Citation, and you'll have a full citation.
This is a wave machine. It's a device I really like using in the classroom, not just because it's fantastic for demonstrating wave phenomena, but because its construction is obvious so students can see how it works. It's cheap to make, and it's really pretty. As you can see, it's made of 3 components: kebab sticks, jelly babies, and duct tape. It took me about 15 minutes to build this, but I reckon if you've got someone helping you, you can do it in around 5. Now, obviously, you could build it in advance, but you could also build it as part of your lesson, or perhaps even get students to make their own. A few things to bear in mind. The tape needs to be in tension, so it needs to be attached to something rigid, and I'm using these clamp stands attached to my bench using these G-clamps. The spacing of the kebab sticks isn't critical, but they do need to be roughly evenly spaced, and I'm using a gap of about 5 centimetres. You can make a slightly more robust and reusable version by just running another length of tape along the top. Now, the one problem you will encounter is that as you're building the thing, it tends to get lopsided. But you can easily solve that by simply sliding the jelly babies along the kebab sticks. So that's how you build a wave machine. Let's see what it can do. I think it's best to start with a single pulse, which you can generate like this. Now you can see that there's a disturbance which travels gracefully from this end of the machine to the other. And the key thing to emphasize is that you can see the jelly babies moving up and down, but they're clearly not moving through the machine. It's the disturbance that goes from this end to the other. So how does that work? Well, when I lift this jelly baby, it causes this bit of the tape to twist, which twists the next bit, and so on along the whole length of the tape. So it's the twist that is moving through the tape. What the jelly babies do is add mass to the system and slow the whole thing down, making it easier to see. So in effect, what I'm doing is putting energy into this end of the machine and seeing it transferred several meters along the machine by the disturbance. I can change the amplitude of the wave by simply lifting the jelly baby higher to begin with. Now, notice that that doesn't change the speed of the wave. If I jiggle the jelly baby up and down more quickly, I should get waves of a shorter wavelength and a higher frequency. And again, notice that that doesn't change the speed of the wave. We can change the speed of the waves by changing the machine. So, I've removed the jelly babies from just over half the machine. Now watch what happens. What I hope you saw is that as the waves cross the boundary from this part of the machine into this one, they speed up, just like light waves speed up as they move from glass into air. So there you have it, a wave machine made with jelly babies.
Okay, that was very cool. So just noticing that, as I said, the particles moving up and down, they're not moving forward, right? So it's just the wave or energy is moving forward. Let's just go back. So here's the sound waves travel from one source to our ears. Sound waves are often considered longitudinal waves. Again, longitudinal. When you speak, you pressure the air, it's your sound pressurize the air and compress it, expand the um, air, surrounding airs, and that's how it's moved forward. For drawing a Okay, so when we're talking about the highest point or maximum point in longitudinal wave, we're talking about more intense. I'm gonna just draw that. So when you're speaking through the air, some part of the air will be very intense, like high pressure. In here is the low pressure and high pressure, low pressure. This kind of we have here, we have maximum. Here we have our minimums and again maximum, right? You see, you can describe it like this. Now, what happens if two sound waves or two waves interfere or comes together? Sorry. The result of two more waves meeting each other at a particular point in a space, we call it interference. Now, two waves can collide at the same point and it could add up or it could cancel out or uh, cancel out each other. So I hope that we have some here. Let's say the wave A moving to the right and wave B moving to the left. And they meet each other at some point, they add up, and you will see a very high amplitude wave. After they interfere, the wave B move to the left, continue moving to the left, and the wave A continue move to the right. So they interfere and they pass along each other at the end. We call this one constructive because these two amplitude add up. Because to have a two positive amplitude, they add up. Now, let's just look at the wave X and Y. They have a same amplitude, but one of that is negative, one of that is positive. When they come together, they cancel each other. So it's a positive and negative amplitude. They cancel and you see a straight line, nothing. After they interfere, the wave X moving forward. That's why to like move wave X continue moving to the right, wave Y continue moving to the left. Okay, they come together, they cancel, and they move away again from each other. So we call it destructive interference because they cancel each other. Now here is, I don't know what is the slide. So yeah, this is the slide. The following slides show two waves meeting at some point in a space. At the same time, we will learn how to determine the resultant wave for each case. Okay, so this is example one. You have wave A and you have a wave B. Wave A is in red and wave B is in orange. Now, I want to draw the resultant. See from here to here, the wave A has an amplitude of 1, 2, 3, 4, 4 positive. And from here to here, wave B has an amplitude of -4. If I want to add them up, of course, they will cancel each other, right? So then from here to here, the interference is going to be destructive. And I put it as a straight line. So all of the wave red here and all of the wave orange here cancel each other and will be collapsed here. Just put a straight line here. And look at the rest of that. From this point to this point, the red one, the amplitude of the red one is 0. And the amplitude of the blue one is -4. So 0 plus -4 is -4. So from here to here, my waves stay as my wave stay as -4. So this will be a resultant of our waves, okay? Yeah. This is another example. We have two waves again, wave A in red and wave B in blue. I want to see how they interfere. So what I can do, I can add them point to point. Like at point 0, both of them is 0, right? So that would be 0. At this point, one of them is kind of 1.5 and the other one is 2.5. So 1.5 plus 2.5, let's put that here. This point, it would be I'm adding their amplitude, okay? It's gonna be 4. So at this point again, sorry, it says 1, 2, 3, 4, 5. At 5 seconds, just here, they add up and the amplitude become what? 5. 1, 2, 3, 5 here. At 10 seconds, here the amplitude of the B will be what? 4. And amplitude of the A is 5. So here is going to be 4 plus 5 is 9. At that second, will be there. I'm going to just add this one. And at this point, or I can do that here as well if you want to have more points. So the amplitude here is 2. And for the other wave, it's 4. 2 plus 4 is 6. Just here. And at that second, again, 0 plus 0 is, they have the same height, right? 0. 0 plus 0 is 0. Is there. I just need to connect the points. It's going to be a straight line. Oops. I think I need to. Here. Okay, I'm going to just erase them. That would be it. So their amplitude add up at each point. Any question?
Yes, I have a question about the first example you did.